All right, Claude, go ahead.
All right, so we got RIP is what we're going to be dealing with tonight. So
Yeah.
RIP is an older protocol, okay? And RIP is, how can I describe this? There are two versions of RIP, if I remember correctly. All right, there's version 1, version 2. And when I remember, so all of us were taught about class lists and classful addresses and things like that. So think about, we were talking about a /24 earlier, which is a nice even number that a lot of us, we may deal with in labs, just for the sake of dealing with an IP address network, for our lab purposes. So think about like this. You take that /24 and you chop it up into something smaller, okay? /27, /25, /29, whatever it may be. There is one of those versions that recognizes that /24, and it also recognizes those smaller versions or those smaller pieces of it that you may use through VLSM to break them down into. And what happens is, it's like you have version 1 of RIP that can basically receive updates from both the versions themselves. So let's just say you are running, and this would be not best practice, but you are running multiple routers in a topology, and you got a mix of version 1 and version 2. Now, here's the thing. Version 1 is going to be able to receive those updates from other RIP routers within the topology, okay? As far as the routes that they're sending, as far as the prefixes they're sending, classful, classless, whatever it may be, chop it up, pieces of a larger one, whatever you want to call it, okay, for you to understand it. Now, here's the problem. The routers in that topology that are running version 2 will not be able to receive all of the updates from its neighbors. Okay, so therefore what happens is it gets pieces of the existing networks that it has access to. All right, so let's just say we have a network that is, like I said, it might be a 1.00 network with a /27. Okay, it's a smaller one. What'll happen is that update will get sent out by that RIP router. Okay, and version 1 routers that are running version 1 will see that and accept that. Routers that are running version 2 will not. Okay, they will not. So like I said, and let me just check and make sure that what I'm telling you as far as those versions.
No, you're right on the money.
Is that the
You're
case?
right on the money.
Okay. So this is where you can see where RIP can actually be a hindrance in some of today's modern networks. Okay, as opposed to using OSPF or EIGRP or something like that for your interior gateway, But we understand that RIP is what's known as a distance vector. So here, where let's say with egrip, you're thinking about changing and manipulating route paths. So you're talking about using bandwidth. You're talking about using what's the other one? Cost. No, cost is OSPF. Let me see, bandwidth and what is the other one for EIGRP? K3 at
Delay.
delay. There you go. Good one, Angela. Delay. So you start manipulating those two parameters, or the K values, K1 and K3, right? And you can actually manipulate your path with EIGRP as far as the direction something's going to take. With RIP, it's a matter of hop count. Now, I remember when we were going through the spanning tree stuff, a lot of people kept intertwining that word hop, okay, when they talk about going from switch to switch to switch. So I'm not going to say to think about it in that terms, but if that resonates with you a little bit better, then I understand that. But like I said, RIP is based on hop count. If I can get from point A to point B with less stops in between, that's going to be the way I'm going to go. Okay. And of course you change. I'm trying to think I think that's the RIP actually has a maximum hop count. It can actually, I think it's like 15 or 16.
15. Yep.
It's 15. Okay. So there's a maximum hop that that a path can be before it's dead. So you can almost think of that as like a real short TTL in a sense. TTL, as you know, the time to live, a packet will bounce and bounce and bounce until that TTL is pretty, either it arrives at its destination or that TTL just expires as increments. Well, when you're thinking about RIP, a packet running through RIP, then think about the TTL being almost like 16. It's going to go from one router to the next router, and each time it hits a different router, different switch, its hop count is being incremented. So if it can't reach its destination within that 15 hop count, you're looking at a possible redesign of some stuff.
Nice. 100%. 100%. So guys, that's very important, right? And I'm going to pull up the lab here in a second. It's very important, the key things that he stated, right? Hop count of 15, right? And why, if we, let's say if RIP was still in, people were using, I hope people aren't using RIP today, right? We have all these, we have VMs and resources that exist on, Amazon, Rackspace, Azure, right? They may be beyond 15, right? And of course, right, our routers may sit even behind some firewalls, right, that they have to go through and go through a couple of ISPs. If we were using RIP now, dude, we barely can get through anything, right? We can, to where I don't have no connectivity. Well, shit, hold on. This might not even be a DNS issue. This may be
it's just too far. It's just too far.
This is just too much. Hey, you can't reach it, So it's so many things that you have to consider, right? And I want you guys to understand the importance of a distance vector protocol and why this is important to understand, because, dude, whenever we jump into OSPF, eGrid, we can config anything all day, every day. But if you don't understand how it works when you're troubleshooting, right? Of course, me, Claude, Kelvin, and anybody that's working in a production environment now can tell you these war stories. It won't even make sense when you're troubleshooting, because you're like, wait, I just worked in a working state whenever I'm, just configuring stuff. But if you don't truly understand the theory, you're going to be confused as much as whoever you're helping troubleshoot it. Right? So, where is it? Desktop 2. Okay. So, right? So let's look at this lab, right? So within this, right, we're doing RIP, right? We have LAN 1, this is on the left, right? 192.168.1.0/24, right? And we have LAN 2, 10.10.1.0/24, right? Within this topology, we're under 15 hops, right? So everything should be working, right? So, right, we all know there's always an election process. There's always a definitive factor, right? let me make one quick point that I said when we were going over, some, IP routing basics, right? IP routing and IP route learning is two totally different things, okay? But they're dependent on each other to the point to where, the industry sums up and says, hey, it's IP routing, right? IP routing is the action of moving packets from one layer 3, broadcast domain to another, right? And moving it to its destination, right? Depending if you're using a static routing or dynamic routing protocol, okay? IP route learning, right, is, that's used by, that's used to define, dynamic routing protocols, whether that be BGP, whether that be OSPF, RIP, etc., right? And so we're going to dive into IP route learning, right, which is what the router is going to do so that it can perform the function of IP routing, right? So we have to understand how this IP route learning works, how it's going to function within this environment. So then, perfect, if we're having IP routing issues, we need to understand how the IP route learning is happening on the back end so that we can go ahead and troubleshoot, right? So remember what Claude said. And guys, please stop in your head if you have a question. I told you whenever we jumped into layer 3, we were gonna have a field day. So, hey, feel free to stop me. Just like Claude said, right? It is, we're gonna go ahead and we're gonna look at this and we're gonna say, hey, less than 15 hops, and this is a distance vector protocol. I'm gonna go, right? I'm gonna take whatever path to my destination, whoever has the less hops, right? Because that's more efficient. That's the metric that I'm looking at, right? And back to what we were talking about, right? Anybody remember the decision factor whenever installing routes in our routing table or our routing information base? Anybody, feel free to answer. What's the 3, deciding factors of how routes get installed into a routing information base or a routing table?
All right, I'll start y'all off. The prefix length was one of them.
There we go. That's the first one, actually. Good stuff. What's next?
The administrative distance.
Anybody? There you go. That's the second one. What's next? There's one last one. I said the word earlier.
Is it the most specific route?
Close, right? It's metric. Okay.
Oh yeah, metric.
So like Claude said, right? Prefix length. All right. Who has the longest prefix match? /24 versus the /28. I'm gonna go ahead and send my packets to the routing protocol that's using a /28. That's the most specific, route that I have in my table to get towards the destination or shoot, packets toward that destination, right? Boom. Let's say the longest prefix match for, 2 routes that I'm getting, advertised into my routing information base, the subnet mask is the same. Perfect. We're going to go to AD, right? So AD, just like administrative distance, just like Angela said, different numbers, right? We have OSPF, we have RIP. RIP is 120. We have OSPF. Claude, keep me honest, it's 110, right? eGRIP, 90, right? So whoever has the lowest numbers is the strongest, right? So there's a reason why RIP is 120, right? It's less reliable than what we use today, eGRIP, OSPF. And of course, Cisco is going to put eGRIP at 90 because of course they create
it's their stuff. Yeah.
It's their stuff, right? So of course, right? So a couple of things you need to consider, right? Let's say, right? And of course, this, Angela, thank you for answering that, right? And of course, what me and Calvin was talking about, right? Metric. Last piece, right? Within this entire environment, the lab that you see on my screen, we're using RIP. So it passes, the first 2 elections. So now we're going to go to 3, metric, right? So now we need to go ahead and do a weight system. We need to go ahead and see, how many hops does it take from R1 to get to 10.1.0, right? What's your better path? Is it through gigabit 0/1 on R1, or is it gigabit 0/2 right, through R1, right? How many hops will it take, right? Hops being layer 3, okay? I know hops are used, that term is used interchangeably within layer 2 and layer 3, but we're going to use hops, the word here. We're going to keep it simple. It's Wednesday, and I haven't had any dinner yet, so we're going to use hops. We're not going to get too technical, okay? So, Brian, right? If we're playing Super Mario Bros., right? From R1 to R4, how many jumps does Mario have to do to get from R1 to R4? Brian isn't here, then Kelvin, how many hops does Mario have to do from R1 to R4? Kelvin's probably muted. Angela, how many hops does Mario have to do from R1 to R4 to get to the castle?
Hold on, I'm trying to see the label on this on the water.
Okay. You need to zoom in? I can.
Which one is Mario exactly?
Say it again.
Which you said Mario? Which one is which water are you talking about? From which side?
Okay, yeah, I got you. So where's my drawing thingy? Okay, where is that? All right. So I'm gonna doodle Super Mario. This is Super Mario, right?
Mm-hmm.
He needs to get to the castle, which is right here. Okay?
Mm-hmm.
Right? So Super Mario gets to R1, right? He has 2 paths to take, right? If we're talking about RIP, right? Right? And we're going to keep it simple. How many hops, right? How many hops does Super Mario have to take from R1 to get to R4 using this top path?
So basically, it's gonna take the lowest hop count. So
Nope, that's not what I asked you. That's not what I asked you. How many hops is it taken from R1 to R4 through the top path?
It's gonna be 3.
Perfect. 100%. So, Angela, what about the bottom path? How many hops would that take? Would Super Mario take?
That's actually 4.
Why?
Hold on. Oh, that's the same path.
It is?
Hold on. 1, 2, 3, 4. That's actually 4.
And how much is the top path?
Give me a second. Yeah, as I said, the bottom one's gonna be it's gonna be the same. It's gonna be the same path. It's gonna be 3 and 3.
Claude, help him out.
Can you hear me now?
And yeah, I can hear you.
Okay. So let me turn my speaker off real quick. All right. So basically, Mario has 2 different paths that he can choose. Okay. He can go up top, he can go down through the bottom. Now, basically, think about it like this. When you hit an egress, consider that to be 1 hop. Okay. So you're looking up top. You got a path of R1 to R2 to R3 to get to R4. Okay. Mario's going to go down to the bottom. He's going to go to R1 to R5 to R6 to R7 to get to R4. Okay. So don't think of them as routers. Think of these as as cities. How many cities are you going to go through the top path or through the bottom path to get to your destination. Does that make sense?
Yeah.
So to reiterate now go back to the question Dave just asked you.
Yeah. Basically, I was telling him it's gonna take the first path. So basically, it's gonna be the top one, which is gonna cost him like gonna be like three hop. So the reason why he's not gonna take the bottom one is because it's gonna when you actually set the traffic, when you actually go ahead and test the route, it's gonna see like it's gonna cost him more than actually than the top one's gonna actually cost him. So basically, he's gonna be like, hey, let me actually take the one with actually the lowest up cap.
100%, absolutely, right? Because if since we're using metrics, right, as our determining factor, right, just like you said, right, and for RIP, right, the metric that we use is hop count, right?
Yeah.
And so, just like you said, and dude, great job, by the way, and Claude, thank you for jumping in to assist. Since the top path, right, has a hop count of 3, has a metric of 3, right? And the bottom path has a metric of 4. Router 1 is going to see, hey, to get to my destination, so for Super Mario, to get to his destination to 10.10.1.0, where the castle is, he's going to take the top path. It has to take less hops. Now, right? How is that inefficient? How could it be inefficient? Right? Let's say that top path has links of 10 megs and the bottom path has 1 gig links. But just because it has less hops, we're going to go ahead and take that.
No. It depends of it depends of the boundary file as well. Because if he has like, is it?
Think about what I said.
So
think about what I said earlier.
So Angela, I'm making a point, right? So you're not wrong. I'm making a point of how inefficient RIP is, and the thing about distance vector. We're using hop count, right? How long it takes, how less of a time it takes to get to my destination. My scenario was, here's an example of it being inefficient. Let's say throughout the top path, to get to 10.10.1.0, it only takes 3 hops, but my links in between, right? Between those hops are 10 megs, right?
Okay.
On the bottom path, it's 1 gigs. What happens if I have a lot of traffic that's exceeding 10 or 100 megs on the top path? What's happening? What's happening for my end users on the 192.168.1.0 network? Some traffic is going to be dropped. We were talking about QoS before we jumped on this, right? With Kelvin. Some traffic is going to be sacrificed, right?
Yeah.
It's going to be sacrificed, right? So this is why, right? Just to make it all come together for you guys, right? This is why, right? RIP is inefficient, right? It's great to understand how distance vector works, right? And this is why I wanted to go over it, but I want to give you guys a real world scenario of why, right? Why they don't use it now in the real world, why, and how it can affect if we did use it in today's world. Make sense?
Yeah.
So let's go ahead and Angela, go ahead.
What you're saying, just like it doesn't matter like if you have like a 10 gig link, a 1 gig, like a 10 meg link, you're just gonna actually go and pick the one that is the less hop count.
100%. 100%. Okay. So that's why that's inefficient, right? And so that's why you have to go ahead and consider, of course, to do your research on these other routing protocols and say, okay, what's more inefficient? Of course, if you guys, I'm sure some of you guys work in the networking or cybersecurity space now. You hop into you guys, router or firewall or what have you, you'll see, protocols like OSPF. Typically OSPF is used. within some environments within the organization, eGRIP can be used, can be leaked into OSPF or what have you. But again, you know, if you see RIP work today, you want to get a great promotion, you know, give yourself a project and promote, you know, hey, why are we using RIP? You know, so you can go ahead and do that. But let's confirm what Angela and what all of us spoke about tonight to see if what Angela answered was correct. Are we taking the top path to get to 10.10.1.0? So let's go ahead from R1, right? And our destination is 10.10.1.0. Let's go through the routing table and see what is it taking, you know, to go ahead and get to it. So, right, like we spoke about, right? Our metric that we use is hop count, right? And so the hop count that we identified on the top path is 3. Hop count that we identified, or the metric that we identified on the bottom path, is 4. We see what got installed to get to 10.10.1.0 is, and of course it made it a /8. Because of course the other piece that Claude included whenever he explained RIP is that you can't identify subnet mask, right? So it's and Claude, keep me honest here. It's you can't identify the class to a T, right? So it's class list. It's going to say, hey, you're using a 10 dot whatever network, we're going to make it a /8. Can't modify it to be a /24, what have you, right? So /8, right, to get to R4, which of course that would cause issues as well. But we're going to take the top path, right, because that has a better metric, right? So that confirms what Angela stated. Hey, we have a less hop count growing through the top. We're going to go ahead and take that path versus R4, right? And let's go ahead and test it. Let's go ahead and start breaking shit. If we go ahead and break R2, right? We should see it's a metric of 4, right? We should see a metric of 4 whenever we're trying to go through R5, right? So if we go ahead and ping 10.10.1.254, should fail because it's going to take a minute as well for, of course, database and everything to be learned, traversed, what have you. Give it a second. Any questions, guys, while we're loading this up and we're proving some theories?
RIP is not like EIGRP where a topology change happens and then it starts to recalculate things automatically on that change. So RIP can be slow to reconverge.
Did you guys hear that, Claude? Because you were kind of far away.
I did.
Yeah, so a lot of times, you start talking about, when you got some kind of failure within the path. So we get comfortable with RIP recalculating, RIP sending out, some additional request. OSPF sends out requests when there's a topology change. RIP is a little slow to do that. Okay. So that's why, when there's a device like basically what he took a device down is what he did. Okay, he took a device down. So RIP updates are sent, let me see.
Every 30 seconds?
30 seconds, yeah. So basically, it's not on demand like with EIGRP or something like that. You actually got to sit and wait it out.
Yeah, question. Since talking about routing protocols, what does ISIS uses for the metrics?
A good question. Let's Google.
Adric is the same thing as OSPF.
Yeah, it's links. Yeah. Let me see here. That's another one that's hardly used a lot. Let me see.
Yeah, it's on the NSTED exam. People who want to work in data centers, because data centers are moving over to ISIS.
Cost.
I'm Googling now, Daniel.
Cost.
Oh, yeah. So
So you
Means
can
a lot,
always
and
take,
thanks for checking that. So we're using cost, so we're using interface cost as well, just like OSPF.
Okay,
So we're using bandwidth.
Okay, with the OSPF, we use a Dijkstra algorithm. That's the same thing as ISIS, or they use a different algorithm for that?
it's going to be a
Say again?
different algorithm. Yeah. Dijkstra is exclusive to OSPF.
Okay.
Oh, he's asking about the algorithm. Okay.
Yeah.
Perfect.
Then EIGRP uses the dual algorithm, all the K values there.
Exactly. And, you know, basically by default, the only K values that we really probably manipulate are 1 and 3.
Yeah, bandwidth and delay.
Right. Yeah, it's a lot to remember.
So guys, if you see it, right, we still haven't had our update yet, right? So you see how slow RIP is as well, right? We got an update, but now it's super confused, right? Hey, how do I get to 10.10, right? I still have in my cache X, Y, and Z, right? So this is an example of RIP in a production environment, right? And so if we're all working for a company, right, and we see, you know, we're using RIP, something like this happens, router goes down, links go down, or what have you, right? By the minute, we're costing the company money, whether that be $100,000 or $1 million a minute, right? So we need things that are so efficient to where if somebody like Daniel or Brian or Kelvin or any of us jumps in and say, hey, we need something that's quick, fast, efficient, that we can troubleshoot, that we can, if we need to reset routes, we can go ahead and do it and it can learn it quick, we wouldn't have no issues. Does that make sense?
Yes, sir.
Perfect, perfect.
Yeah,
Well,
one of my Cisco professors said, if you get a job with using router RIP, look for a new job.
Mhm.
He said. I said, okay. He said, router RIP is a nightmare to try to troubleshoot.
Dude, I would keep that job. That'll be a design opportunity for me. Shoot. But guys, that's it, man. That's it. Any other questions? I didn't want to keep you guys too long. RIP isn't widely used, so there's no need for us to dive into it. But I want you guys to understand how, you know, the origins of distance vector and how this came into play before, you know, the distance vector that's widely used, which egrep is used. Ooh, I'll take the silence as it does.
Hey, real
And
quick.
on that note,
real quick.
Yeah, go ahead.
Real quick. Can you pull up the CLI on one of your RIP routers and then actually pull the actual config up?
Yeah, let's do it. There we go.
Yeah, do it. There you go.
Down.
Yeah. So you see that right there. So he's specifying version 2 here. Okay. And I think by default, no, I think version 2 is the default. So you can actually specify version 1 if that's what you're wanting to do when you're putting your stuff together.
Isn't version 1 a class 4 routing protocol?
It is.
Classless?
It is. It is. Yep. Yep. So if you are designing RIP networks, you know, you just keep that in mind. If you want subnet mask information to be sent out to his in his updates, you thinking of version 2. If you want to stay classful with these big massive networks, then you thinking of version 1 when you're putting that together. But yeah, good stuff, Dave.
Hey, this was a team discussion, so I can't take the credit. Claude, thank you. Everybody, thank you for your questions. I hope this makes sense because, guys, we're gonna get deep. We're gonna get deep whenever we're jumping into layer 3, right? And I think Antoine had the question earlier. You know, shout out to Antoine. You know, he was asking about a layer 3 technology, right? Transport technology, MGRE, right? But of course, as I'm going to tell all you guys, and even I tell myself all day, every day, and Claude and Kelvin and whatever, all of us, we tell us there's building blocks before we get to that, right? just like I tell you guys whenever you guys should be whenever you're troubleshooting, or any of us are troubleshooting, the OSI model is there for a reason. There's building blocks for everything. If client comes up, oh, I can't get to such and such, and you automatically jump to layer 3. Well, damn, how do you know a cable isn't out, right? So we're going through these building blocks. It's going to be a little bit slow, right? But there's plenty of things that we need to learn before we go ahead and jump into things like DMVPN, like different types of multicast, VPN tunnels, right? A whole bunch of things, right? So we're going to go through this for a while. It's probably going to be 2, 3, 4 month thing, depending on how deep you guys want to get with BGP, and Claude will have a field day with his lightsaber on that one. But right, be ready, guys. Keep labbing, take breaks, because again, this is a lot of information to take in. And guys, I'll see you guys in 2 weeks. Now, I am going to stop sharing and stop the recording. I know Kelvin did have a question, so let me go ahead and stop the recording.